Hello everyone, I'm Zhao Zian from Beihang University. Today I will introduce CLOI, loop transformation over fully homomorphic encryption via multi-level vectorization and control path reduction. First, we introduce the concept of FHE compiler. Given an input program written in C, for example, the FHE compiler applies FHE-specific transformations and optimizations in the intermediate representation. Specifically, in this program, n plaintext multiplications can be transformed into a single multiplication on ciphertext, resulting in better performance for homomorphic computation. Finally, the program is bound with proper security parameters and translated into APIs defined in FHE libraries. In summary, automating homomorphic computation through an FHE compiler is essential to make FHEs accessible and usable for non-experts. In summary, FHE compiler workflow can be divided into three stages. In the front end, the compiler translates the input program into FHE IR. In the back end, the transformed program is processed for parameter optimization and FHE library mapping. Meanwhile, CLOI primarily focuses on the middle end, which involves rewriting the program into a more specific friendly form, particularly through analysis of control structures. Since loops with complex branch structures are inherently inefficient in the FHE programming paradigm, CLOI proposes several optimizations, including loop segmentation and branch reduction, to enhance the execution efficiency of loops. To illustrate the challenges in handling loop structures, we provide an example program for clarification. In this program, the loop condition of the first loop is not encrypted, while the second loop is encrypted. The first loop is referred as a transparent loop. The difficulty in processing transparent loops stems from the mix of arithmetic operations such as additions and multiplications, and logical operations such as comparisons, making it challenging for vectorization, while the second loop is referred as an oblivious loop. The primary challenge with oblivious loops is the inability to determine loop termination and branch passes, requiring the traversal of all potential iterations and branches. For transparent loop optimization, the core idea is to distribute a complex loop into multiple simple loops, each containing only a single type of operation. In this program, we can segment the operations within the loop body into a logic part and an arithmetic part. Based on this segmentation, the loop is decomposed into two independent loops. For the logic circuit loop, which involves purely comparison operations, we introduced the CMD programmable bootstrapping technique to enable batch comparison. For the arithmetic circuit loop, it can be transformed into a classic rotation-based accumulation procedure. Through loop segmentation, CLOI achieves vectorized transformation of the loop body. In the benchmark evaluation section, our comparison focuses on the efficiency of CLOI, HARE, Transpeller, and Paxos. By evaluating various arithmetic circuit benchmarks, we observe that CLOI significantly outperforms the other works. This improved performance is attributed to the loop segmentation and vectorization technique employed by CLOI. For oblivious loop optimization, we consider two scenarios. If a loop body can be transformed into Gauss-summable or C-finite recurrences, we can use a recurrence solver for closed-form expression. The exponent term in these expressions can be evaluated by blind rotation. Otherwise, for generic oblivious loops, we propose two approaches for branch optimization to batch the evaluation of loop conditions. Equality test-based branch optimization can be implemented through polynomial approximation or SIMD programmable bootstrapping technique. External product-based branch optimization, on the other hand, is effective for RGSW ciphertext with exponential encoding. In the oblivious loop benchmarks, we compare the latency for evaluating 5 different applications. For programs that can derive clues from expressions, such benchmarks run extremely fast on CLOI. For the other benchmarks, will other compilers require comparison operations in every iteration? The branch reduction strategy of CLOI achieves better latency performance. While CLOI provides better performance for FHE programs with loops, these optimizations do come with some limitations. For instance, as shown in the figure, the use of SIMD programmable bootstrapping technique, while significantly speeding up execution, also increases memory usage. Additionally, when loops contain complex nested dependencies, it becomes harder for CLOI to fully leverage its vectorization capabilities. These are areas we are actively working on to make CLOI more robust and efficient. For further details of this work, please refer to our paper. The source code of the CLOI compiler is available on GitHub. If you have any questions, please feel free to contact us.